So now that we've talked about the try-advance method, it's time to talk about the really interesting method here, the try-split method. And try-split is what's used with the parallel version of this in order to take a work of Shakespeare and break it up into smaller chunks. So we're going to use try-split, or rather more specifically, the streams framework is going to use try-split to partition a given work of Shakespeare into chunks, multiple chunks, that can be searched in parallel. And it's going to use all these little helper methods to do this. Here's the try-split method. That's the one that is actually defined in the Spliterator interface. And then to implement try-split, we're going to have all these helper methods that we write in order to handle things like not splitting the chunks across a phrase boundary, which would be a bad thing. Notice something when we look at this. There are no locks. There's no synchronizers in any of this stuff. Splitterators, even parallel splitterators, all work effectively in a single thread of control. This is a quick pseudocode synopsis of how this is going to work. And this is very similar. Almost every try-split method does something along these lines. So here we have the original input string, which is a work of Shakespeare. And the splitterator is going to try to split things as evenly as possible without having to worry about splitting across the elements. Now, one of the things to note here is that try-split doesn't need to be perfect in order to work. So what it's going to do is it's going to check to see at any given point, is the input we're looking at below the minimum size? If it is, we're just going to return null. There's no sense splitting past a certain point. Unlike all the other splitterators we've looked at so far, where they split down to atomic-sized elements, like every element in an array list, this splitterator is going to have a much larger size be its minimum size. Because as I mentioned before, there's no point in doing word searches on very small strings, because string searching is very fast. So if it's below the minimum size, return null. That says we're done. Do the try-advance method henceforth. Otherwise, it's going to split the input up into two relatively even-sized chunks. The operative word is relatively even-sized. And return a splitterator to the left chunk after updating the current object to account for the fact that we just got rid of its left side. As I mentioned before, you don't have to split entirely evenly in order for this thing to work efficiently. So this is what the actual code looks like. And I left a few things out just because it would get too messy, but we'll walk through it and I'll show you the key parts. If you really want to see the code in all of its full-blown glory, take a look at the implementation stuff in my GitHub repository. It's very heavily commented and it will explain even in further detail. So if the length of the input at this point, which may have been split several times, is less than or equal to the minimum split size that was computed in the constructor, we're done. So return null. Otherwise, let's take a guess at the initial split position. What better guess to start with than the length divided by 2? So all things being equal, let's split things in half, because that'll give us the best evenness for the splits. We then go ahead and we go ahead and compute the start position, and that's our initial guess. So compute start pos is going to go ahead and take a shot at trying to split things, and then we'll do some other stuff to update the split if there's going to be an overlap. So here's what compute start pos do. We take that initial guess, which is half. We figure out what's the length of the phrase we're dealing with. Is it a long phrase? Is it a short phrase? Is it a long phrase like Hamlet's to be or not to be soliloquy, the whole thing? That would be rather huge. Or is it a very short phrase like anon, which he uses a lot? So we figure out the length, and then we take the split pos, and we subtract the phrase length. So here we go. Let's say, for sake of argument, that we had Hamlet, and for some reason, halfway through Hamlet was of, and the second half starts with wit. So if this is the guess we did, we have the start pause and the split pause. So here's the split pause right there. That was our initial guess halfway through. We compute the start pause, which is then some number of bytes back. It's the phrase length minus the split pause. And then we just do a little bit of sanity checking to see whether or not we even need to go ahead at all. And if the phrase is too long for this input segment, we're going to bail out and let it go and do searching with sequential streams, or with the sequential try-advance, rather than trying to split this up at all. Otherwise, we return the start pause. So the start pause is the split pause minus the length of the phrase. We're doing this, by the way, to make sure we don't end up splitting across the phrase itself. So we return the computed start position. We then call another method which will update the split pause if the phrase spans or straddles the initial split pause. So we need to update split pause if there's going to be a problem. So we pass in the start pause and the split pause, and then we get back an updated split pause. Here's what try to update split pause does, pause being position. So keep in mind, starting out where start pause is here and split pause is here, and this is the phrase we're searching for, brevity is the soul of wit, and there's where we've attempted to split things in half. The whole purpose of this method is to avoid splitting a string, an input string, across a phrase. So what we do is we have this new field, this new variable called npause, which is the split pause plus the length of the phrase we're searching for. So this tells us where the very end of the input is that could match the pattern. So what we're going to do is look from here, from start pause to end pause. We're going to look to see if the phrase is anywhere within there. And the reason we do that is because it could straddle at various points. If the phrase is not longer than the input string, we're fine. If the phrase is longer than the input string, then again, let's just bail out and not do any more splitting. Here's where we get really clever. We go ahead and we extract a substring from the start pause to the end pause. So that's going to be the unit we're going to look to see if the phrase exists anywhere within that range. And then we make ourselves a new pattern matcher for that substring, and we're going to see whether or not this pattern we're looking for, which in this case is going to be, brevity is the soul of wit, we're going to see if that exists anywhere within the string. And if we do a find on this thing, if there's a match, then that means that the phrase indeed did occur between start pause and end pause. So in that case, what we're going to do is we're going to take the place where we matched, and we're going to end up adding the length of this phrase, and that's going to be the new split pause. And so you'll see what we're going to do here is the final split pause is going to be adjusted so that we're going to move it over a little bit. So rather than splitting between of and wit, we're going to split it so that we end up with split pause being after where the phrase matched. So we don't end up missing a phrase because we split the string incorrectly. So we return that split pause. That's now the new value that we're going to use. And then we're going to use this other helper method called split input to split the input into a left-hand splitterator and a right-hand splitterator, which will then be further split or processed by tryAdvance. And here's what split input does. It takes the updated split pause, which now doesn't straddle the phrase we're looking for. It goes ahead and it makes a subsequence of the input that covers the entire left-hand part from 0 to split pause. That's the left-hand part. And we then go ahead and update minput, which is now going to point to the split pause to the length of the input. So it's going to be this entire right-hand part. And then we're going to go ahead and update the pattern matcher so it'll only cover the right-hand part. We're going to update the offset to be the split pause. And then we're going to go ahead and return a new PhraseMatchSpliterator that covers the left-hand part. That's the part over here. The right-hand part has been updated here to only cover the portion after the split. So what then happens is we're splitting things up, these phrases, these substrings up into chunks, so the original input string up into chunks, substrings. We're then going to have those things get handed off to the common fork join pool, and then that will go ahead and run those searches in parallel, while also searching for phrases in parallel, while also searching each input string in parallel. So now we've got parallelism galore. So that's the end of the overview of the try-split method. I think you'll agree it's very subtle and tricky, but it's a really great example of using splitterators to good effect to get more parallelism in the program.